This lecture video pertains to the topic of trig integrals. We have discussed integration by parts. Trig integrals, in terms of formulas, will involve two tables. The second page of the formula sheet will involve formulas, some identities that we'll need, and additional formulas that we derive together in class. The third page of the formula sheet, this table is for the section on trig substitution. So we will not use this table in the section on trig integrals, but the third topic of trig substitution. This last little section is the final section, partial fraction decomposition. But we are going to go back and focus mainly on the trig integrals. In your lecture packet, I have the fact that the trig integral section is broken down into 5 Roman numerals. And so the first type of problem would involve powers of sine and cosine. The second one, products of sine and cosine. The third one, powers of tangent and secant. The fourth one, products of tangent and secant. The fifth one, alternative methods for powers of sine, cosine, tangent, and secant. And with these methods, we can avoid the methods above, perhaps, and approach some of the same problems above, but in a different method, alternative methods. As you can see in the lecture packet, I have the problems and I have the answers. But we will present the work for these correct answers. Before we are ready to dive right in and just start working the problems, I'd like to give you a little bit more background information pertaining to how this is divided up into 5 Roman numerals. So I will write information out for you. If you remember, I gave you an insert from a textbook. So I'll say textbook insert. And the first section there is devoted to trig integrals. This is how I know that particular section can be broken down into 5 Roman numerals. What I do is I follow my bullets. For example, the first topic or first Roman numeral, integrating powers of sine and cosine. That is why I have listed that here. Powers of sine and cosine. Then, if you look to your second Roman numeral, or second bullet, which leads to your second Roman numeral, integrating products of sine and cosine, and there is a table that is associated with this type of problem, second Roman numeral. There also, under the second Roman numeral, is another type of product of sine and cosine to discuss, and that's when the products look like this. Sine times cosine, sine times sine, or cosine times cosine. And you'll use trig identities for those types of problems. They are still products of sine and cosine, but the understood exponents are now 1. So there's 2 types of problems under Roman numeral number 2 dealing with products of sine and cosine. One involves a table, the other involves these identities. Third Roman numeral, or third bullet, powers of tangent and secant, and you have more reduction formulas. Fourth Roman numeral, and it involves a table, integrating products of tangent and secant, standard form. And then the fifth bullet, fifth Roman numeral, an alternative method for integrating powers of sine, cosine, tangent, and secant. So what this means is if you wish to not have to use the reduction formulas for these, there may be an alternative way to solve these types of integrals involving powers of sine, cosine, tangent, and secant. So as I started to say just a moment ago, I was writing this out for you. You've got Roman numeral number 1, and it is entitled Powers of Sine and Cosine. And that involves a reduction formula for sine x to the power of n and a reduction formula of cosine x to the power of n. So there are formulas for these. You must notice that, as it says here, n, which is your exponent, has to be greater than or equal to 2. If n is 1, then we know the antiderivative of just basic sine x and basic cosine x. But to really use the reduction formula, we want n to be positive integer greater than or equal to 2. Greater than or equal to 2. They have the reduction formulas for powers of sine and cosine, and they go on to prove the formula for the sine squared and the cosine squared by plugging into the formulas. They do that for n equals 2. They do that for n equals 3. And then they do that for n equals 4. You cannot see this, but in this particular textbook, they have boxes around these final formulas here, and they were shaded lightly or highlighted in blue, and I call them blue box specials, just for fun. But these particular formulas that we have boxed, they were derived by using the reduction formulas on this page. And then if you look at your corresponding formula packet, and you look on page 2, you have this is Roman numeral number 1. You have the reduction formulas for sine to the power of n and cosine to the power of n greater than or equal to 2. And that's Roman numeral number 1. And then specifically, they have proven when n is equal to 2, here's your blue box formula for sine squared and cosine squared. And then they've proven by formula when n is equal to 3. Here's your formula by using the reduction formulas. Here's your formula for sine cubed and cosine cubed. They also have the formula by using the reduction formulas for sine to the 4th and cosine to the 4th. Again, they were able to get all of these formulas or blue box specials by using these two reduction formulas where n is greater than or equal to 2. I will show you how they derive a few of these, not all of these, but a few of these once I go over the structure of all of the 5 Roman numerals and the types of problems that you will face. Now, going back to the notes, the second Roman numeral will be called, and you go into your textbook insert, like I said, products of sine and cosine. There's actually 2 types. The first one will involve a table, and the integrals will look like this in standard form. Excuse me, that's sine of x to the power of m times cosine of x to the power of n. And they say that m and n have to be positive integers also. And again, it involves a table. Make sure you correct this so that it looks like an N. Sine of x to the power of m, cosine of x to the power of n. The table that you will refer to is in your formula packet, and it is this particular table. So this is why it's got to be in standard form for you to, it depends on if n is odd, m is even, and n is even. And the bullets tell you what to do with the problem stepwise when you face these different situations. So it has to be written as sine to a power times cosine to a power. Now the second type of product of sine and cosine involves this, which involves identities. And we will work with sine of mx times cosine of nx. We will work with sine of mx times sine of nx. And we will work with cosine of mx times cosine of nx. If you notice, the understood exponents here are 1 is the argument that changes, mx, nx. And the way that they actually approach these types of integrals, still products of sine and cosine, is not a table, but like I said the identities, and it's these identities. So if you have an integrand of, excuse me for that pop-up there, I apologize for that. If you have an integral that involves sine of mx, cosine of nx, which is alpha is mx and beta is nx, you can rewrite that so that it looks like this, and you can then solve the integral or find the antiderivative. So we're going to use these identities from trigonometry to rewrite these products of sine and cosine, and that will help us to easily find the answer. So what I will say here is on the formula sheet, it's on page 2, and your identities will be listed here. So when you need to do that type of integral, product of sine and cosine, here are your trig identities so that you can rewrite these products of sine and cosine, or sine and sine, or cosine and cosine. Okay. Roman numeral number 3. If you go to the third bullet in the packet, it says integrating powers of tangent and secant. Powers of tangent and secant. Again, you will have reduction formulas for tangent, and I'll just put a box to indicate there's a reduction formula that goes there, and secant. Those particular formulas, which I call reduction formulas, well, they call reduction formulas, they are on the second page of your formula sheet, and they are here. The textbook goes on to use these reduction formulas to prove the antiderivative of tangent squared, secant squared. Tangent cubed and secant cubed. Notice how they also prove tangent to the first power, secant to the first power. They do not use the reduction formula for those because, once again, here, n has to be a positive integer greater than or equal to 2. And we will go over what they do in this case to prove these two very special integrals, because the understood exponent is 1, and you cannot use the reduction formulas. It only applies to n greater than or equal to 2, positive integers for n greater than or equal to 2. But that is your third category or third bullet. Going into the fourth type of problem. products, I was going to say powers, of tangent and secant. And this is going to involve a table. The general form is tangent of x to the power of m times secant of x to the power of n. And you'll wish to put that in standard form. In terms of the actual packet, it's grainy, but the formula sheet looks even better. You can see that they have tangent first and then secant. Again, you have to worry about if n is even, m is odd. If m is even, n is odd, and then it tells you what to do. I love the tables because it tells you step-by-step process. If you go to your formula packet, that table for products of tangent and secant is much easier to read, and it's located here at the bottom of the page. And that's Roman numeral number 4. Okay. Then Roman numeral number 5 would just be alternative methods. To solve for the powers of sine, cosine, tangent, and secant. So that's the overview of the entire section. And I have examples for every Roman numeral. In terms of your insert from the textbook, this 5th Roman numeral is located here. Alternative method for integrating powers of sine, cosine, tangent, and secant. And again, what this means is if you have an alternative formula for like sine cubed, which we have a formula now for sine cubed because we used the reduction formula on the first page. So originally for sine cubed we had to use this. Now Roman numeral number 5 says there's an alternative formula for finding the antiderivative of sine cubed. That is the general overview of the section on trig integrals. Looking at the formula sheet, I now basically want to prove some of these famous ones called blue box specials, and that will involve us going back to some of these Roman numerals. So this is what I have for that. I have, and this is before we even begin starting problem 1, problem 2, so forth and so forth in the lecture packet. I have some documents that are not in your original lecture packet, but I wanted to go through the process of proving the blue box special for cosine squared. Because if you look at your formula sheet, they use the reduction formula. This is Roman numeral number 1. They use the reduction formula to prove that this is now a blue box special. And there it is. What was that? Cotangent squared. So they have this as the blue box special here. And there's another way to write that final formula also, and we'll discuss that, which is basically this one. So here's the proof. I just thought I would show it to you and talk about it. This is the actual blue box special. This is me plugging into the formula. So here's the reduction formula. Everywhere I see n, I'm going to put in 2. So 1/2 cosine x to the 2 minus 1 times sine x plus 2 minus 1 over 2, antiderivative of cosine x to the 2 minus 2 with respect to x. As you simplify, this is 1/2 cosine x sine x plus 1/2 antiderivative of cosine x to the power of 0. And that's a 0. Which, raised to the 0 power, this is just going to leave you with an understood 1 here. And the antiderivative of an understood 1 is x. So this becomes 1/2 x. So 1/2 cosine x sine x plus 1/2 x plus c. You could stop here or even stop here and say that's the blue box special or blue box formula. But if you want to work the problem so that it's even more condensed using a single trig function instead of sine and cosine, you can multiply by a form of 1, and here it is, 1/2 times 2. And so I'm working with this part here. Originally it's 1/2 times sine times cosine. And now I'm going to multiply by a form of 1. So it's 1/2 times 1/2 times 2, which is 1, times sine x times cosine. By multiplying by a form of 1, I do not change the problem. But this 1/2 and this 1/2 is 1/4. And then 2 sine x cosine x is my double angle formula for sine of 2x. Either one is acceptable, except this one is better because it's more condensed and it involves one trig function instead of 2. How did they do that? They used the double angle formula and they put in a form of 1 as to not change this one. Putting in the form of 1 allowed us to go to this one. So there's the proof. Now, will you ever have to go through the reduction formula again to prove the blue box special for cosine squared on the formula sheet? Absolutely not. What you would have to do on your test is the following. I would expect you to do this as a test question. And after you do your u sub, what happens is this becomes cosine of u quantity squared. And then you would go directly to your formula sheet and you would just state the formula. Obviously, if it's in terms of, cosine of u quantity squared, your formula is in x. So you would do 1/2 u plus, it depends on which formula you use, plus 1/2 sine u cosine u plus c, or 1/2 u plus 1/4 sine of 2u plus c. And after you do that, you go back and you finish it up and say, well, u was 4x, and you can quickly get the answer. So I'll show you that also. So this is more of a test question. Here's the proof. So this is a test question. Once I change everything over to u, I'm able to see that there's a blue box special for it. Let me zoom out. So I did my u sub. And now I have to recognize there's a blue box special. And I know the blue box special says 1/2 x plus 1/4 sine of 2x, but this is going to be 1/2 u plus 1/4 sine of 2u. And the last thing I do is I distribute the 1/4 to this, and your final answer, and I go back to x because u is equal to 4x. This would be your final answer for the problem. 1/2 x plus 1/16 sine of 8x plus 2, because u is equal to 4x. So that would be more along the lines of a test-worthy question, not the fact that you have to prove the blue box special for something basic like cosine squared, but to then go a little bit further and do a problem like this, in which after u sub, you can go directly to the blue box special. Now the next problem is that I'd like to show you. You have blue box specials on your formula sheet for tangent and secant. The blue box special for tangent is natural log of secant plus c. The blue box special for secant is natural log absolute value of secant x plus tangent x plus c. And what they did here is they used u sub. Here they multiply by a form of 1. We cannot use the reduction formula because n is equal to 1. So we have to apply an alternative method here. And I'll show you where these are located once again. You will never have to derive the blue box special for just plain old tangent or plain old secant. But it is nice to be able to show how they did come up with these formulas. Again, they could not use the reduction formulas because n was equal to 1. So this is what they did instead. I'll write that out for you on paper. Here we go. So here's the proof of tangent. Don't ever do it again. But you will have to know there's a formula. So this is what they did. They rewrote it as sine over cosine. And they let u be cosine x. Letting u be cosine x, du is negative sine x dx. So I would need a negative on the outside and a negative on the inside for my u sub, so that this is 1 over u du, which is negative natural log absolute value of u plus c, which is negative natural log absolute value of cosine x plus c. And how they get the blue box special is they take the negative 1 and make it an exponent. Lots of grouping symbols will be very helpful. So they get the natural log of 1 over cosine. And I guess I should put absolute value bars. And then that is the natural log of absolute value of secant x plus c. So that would not necessarily be a test question. What would be test question worthy would be for you to give me the antiderivative of tangent 5x plus 1. Using now the blue box special. After u sub, u is 5x plus 1, you could go directly to the formula. Obviously, it'd be natural log absolute value of sec u plus c. But this is test worthy. Now the other one, for proving secant, what they do is they multiply by a form of 1, and the form of 1 is secant x plus tangent x divided by secant x plus tangent x. And I'll be honest, you may not necessarily know that's what you would have to do, but this is how they proved the blue box special for it, and it's completely legal to do so. So if you distribute in the numerator, you get secant squared plus secant x tangent x, all divided by secant x plus tangent x. What you're going to do is you're going to let u be your entire denominator. You're supposed to have these memorized, but in Calculus 1, you're supposed to memorize that the derivative for secant x is secant x tangent x. And the derivative for tangent is secant squared x. What happens is this is your entire numerator. So this becomes quickly 1 over u du, which is the natural log absolute value of u plus c, which is the natural log absolute value of secant x plus tangent x plus c. And there's your blue box special. So this is not test worthy. What is test worthy is this. And after you do your u sub, u is 6x plus 5, you'll have secant of u, and you can go directly to the blue box special. But in secant u plus tangent u, of course, with u being 6x plus 5. So there's the proof of the antiderivative of tangent, antiderivative of secant. Again, those are both blue box specials. And the one that you see here for tangent squared and tangent cubed and secant cubed, they use the reduction formula to derive those. We have done this one a lot of times in class, the one for cotangent. The proof for cotangent cubed is this one, and the proof of cosecant is this one. We can go over those if you wish, or you could just go over go to the blue box specials. Again, we've done this one in class. All three of these are very similar to what we did for the antiderivative, just tangent u, antiderivative above for tangent cubed, and then the antiderivative of secant u. Very similar things there to derive those formulas. Okay, with that being said, I want to draw your attention to one more problem, and then I'm going to stop the video and then make a second video. Don't want to include too much in one video. But here is the proof basically for secant cubed, and here's the reduction formula, and this is what they get for their blue box special. And again, I'm just going to show you the proof for secant cubed using the reduction formula. So let me write that down. And it does help to see the formula, obviously. That's going to be secant 3 minus 2 is the exponent. Okay, so plugging into the formula secant cubed, we have secant raised to the 3 minus 2 power times tangent divided by 3 minus 1 plus 3 minus 2 over 3 minus 1. Antiderivative raised to the power of 3 minus 2. Okay, so I'll remove that. And this is going to become secant x to the first power times tangent x divided by 2 plus 1 divided by 2 antiderivative of just secant x with respect to x. So this is 1/2 secant x tangent x plus 1/2. Now what we can do for this one is use the blue box special for secant, which we just derived. And that blue box was so your final blue box special for secant cubed is 1/2 secant x tangent x plus 1/2 natural log absolute value of secant x plus tangent x plus c. And that's what they have now for the blue box special. You will never have to derive secant cube ever again. So again, this one was a blue box special for us to be able to go directly to this step, and it made the proof of secant cube that much easier. So you can use blue box formulas to prove other blue box formulas. Now, something that's test worthy would be this particular question. Secant of 7x quantity cubed. Again, after you sub, you let u be 7x and du is 7dx, and you change this to secant of u quantity cubed. You could go directly to the blue box formula, but in terms of u, not x. and you could write down the formula, and then the final thing you do for your final answer is go back to x by remembering that u is 7x. So that's more of a test question, not for you to derive the basic formula for secant cubed, but for you to be able to use the formula or blue box special for secant cubed. That would conclude this particular video. I will have another video that will be very helpful, and I will show you the proof of a few more of the blue box specials that are on your formula sheet. And I think it'll be helpful and help you understand more along the lines of how they come up with these particular formulas. Thank you very much.